The Central African Copper Belt is the largest sediment-hosted copper deposit known on Earth. It is located across Zambia and the Democratic Republic of Congo, and has been developing geologically for over 800 million years, amongst other smaller deposits across southern Africa. Since the 1930s, the belt has been mined as a source for many minerals including copper, cobalt, silver, lead, zinc, platinum, and palladium. The area produces 11% of the world's copper supply and is the world's largest producer of cobalt. The need for these metals, particularly cobalt, has risen as fossil fuel-instigated climate change concerns have sparked a shift towards greener energy. However, converting to greener energy still involves heavy industrialism since batteries, the main component of any greener energy, comprise almost entirely of metals that require industrial mining and processing. This makes large mineral deposits, such as the Central African Copper Belt, an increasingly important natural resource. But how did such a large mineral deposit form? Several detailed theories exist, but here I will summarize the main geological processes that produced the Central African Copper Belt. To set the stage 800 million years ago, the area destined to become the Copper Belt began in a saddle zone between two cratonic regions, meaning a lowland between two older and colder areas of thicker lithosphere, visible as topographic highlands. These are the Congo Craton to the north and the Kalahari Craton to the south. This topographically varied area is referred to as the Lufilian Arc, where tectonic rifting occurred, creating a basin of thinned crust where divergent tectonic plates to the north and south of the arc pulled apart. This basin then became subject to intermittent flood events of ocean water, causing wet to dry cycles. As ocean water evaporates, its salt remains as a precipitated mineral over time. These precipitated minerals, or evaporites, build to produce a sizable salt deposit. This deposition process is documented in the area's stratigraphy through the presence of evaporites along with other sedimentary deposits, as the basin is also filled with eroded material from the highlands. Additionally, as the crust thins, it is warmed by rising magma, which is evident through mafic lava flows preserved in a stratigraphy, with the combination of evaporites, eroded iron-rich sediment, and mafic material filling the basin. Available ingredients for mineral precipitation were plentiful. Fast forwarding to 550 million years ago, the tectonic plates that were pulling apart inverted and began to converge. All of the depositing layers were squished together, and the convergence caused an orogenic collapse of thick and softened crust to form in the basin. These folding and compressing deposits were also continuously being warmed from hydrothermal activity, and generated minerals indicative of both igneous and metamorphic processes such as talc, kyanite, and quartz. Then around 300 million years ago, the most important step in the process occurred: metasomatism, a chemical weathering process that causes an existing mineral to be dissolved and replaced with new minerals. The involved material was hot, compressed, oxidized, and up to 50% saline, and the pre-existing minerals of talc, kyanite, and quartz had hydrothermal veins of hot, salty, oxidized acidic fluid. The volatile fluid caused the minerals within the original rock to dissolve and be replaced with new heavier minerals such as copper, cobalt, and several other minerals that all precipitated from the original dissolved evaporites. A summary of these steps can be seen by viewing the Katangan supergroup, the name for the stratigraphy in the Copper Belt region. The bottom represents the oldest phase when the basin rifting was divergent and pulling apart. These sediments are characterized by igneous rocks from rising magma under the thin crust, evaporite layers, and others, and sediments deposited from eroding basin walls. Above this is where the basin passively went through longer wet-dry cycles, causing further carbonates to form. The newest top layers depicted on this stratigraphy are from 573 million years ago, when the convergence and thickening began. In this way, a chemically volatile area was created deep within the Earth that allowed for the Central African copper belt to form and later become one of the biggest mineral deposits in the world.